Hey guys, it's Miss Rainey. Today we're going to learn about reaction rates, and that includes factors that affect the rate of a reaction and reaction rate diagrams, so how we can read a diagram. Let's get started. So first of all, reaction rate. Rate is how fast a reaction occurs. So that's the change in concentration per unit of time. Remember, concentration is molarity. That's number of moles in a liter. And time can be seconds or hours or minutes or just some time thing. Reactions can be fast, like vinegar and baking soda react really quickly, or slow, like iron rusting. And so we're going to look into what makes them fast or what makes them slow. So first of all, the collision theory says that for a reaction to take place, reactant molecules must collide. So the reactants have to hit each other or come in contact with each other in order to make products. There's more reactant molecules at the beginning of a reaction than any other time, so the reaction starts quickly. The rate of the reaction depends on the number of effective collisions, and to have an effective collision, you must have correct orientation and sufficient energy. So let's think of it this way. If you were going to build a Lego tower, the first thing you would want to do is put one Lego on top of another. So what if you put one Lego on top of another like this? So notice that these two Legos are not going to build you a very good Lego tower because they don't have correct orientation. You've got the blue Lego on top that's upside down on top of the green Lego on bottom. So this, even though these Lego molecules are connecting with each other and colliding with each other, they don't have correct orientation, and so they won't make a good product. So the other thing that you have to have is sufficient energy. So let's say you got your Lego molecules turned the right direction and you put them on top of each other like this. Well, you're still not going to build a very good Lego tower because you haven't given them sufficient energy. You haven't given them that click that makes the tower tall. So, in order to have an effective collision, in order for your reactants to make products or your Legos to make a tower, you have to have them facing the right direction and give them sufficient energy so that they look like this. Ta-da! A Lego tower. And then I can keep building Lego on top of Lego on top of Lego. And I'm going to build a tall, tall, tall tower of Legos and Legos and Legos. So there's a couple of factors that affect the rate of a reaction, and the first one is concentration. So concentration is the number of moles or the number of molecules of a particular thing in your container divided by the size of the container or the volume of your container. So if you have a greater concentration, that means you have a greater number of moles, which means that you have more things in your container, so the reaction is going to happen quicker because they will collide more often. So increased number of moles means increased collisions. And the more collisions you have, the more likely those collisions are going to be effective, which means the more likely you are to make products. So increase the concentration, increases the rate. Remember that rate and time are opposites, so if something is going faster, it's taking less time. Increase the concentration, increase the rate, but decrease the time. Another factor that affects rate is temperature. And so remember that temperature is kinetic energy. And kinetic energy is the energy of movement. Kinetic energy is the energy of movement. So the higher your temperature is, the faster that you are that you're moving. So imagine you had cars that were colliding. The faster your cars are moving, the more likely they are to collide. So moves faster, collides more often. And if it collides more often, then it's more likely to have effective collisions, so the rate will increase, and the time required will decrease, because if it goes faster, then that takes less time. Then we have surface area. So surface area would be like if you had a beaker of water and you were going to try to get sugar to dissolve in your water. So let's say in one beaker you have a sugar cube, and the other beaker you have just crystal sugar, like a packet of sugar. And so if you have a packet of sugar, you've got a whole bunch of little sugar crystals all at one time touching the water all at one time, and it's going to dissolve at a particular speed. But if you have that sugar cube, the sugar that's right there in the center is not going to touch the water until the sugar on the outside has already dissolved. So that sugar on the center won't be able to collide with the water until the sugar on the outside has collided with the water. So with this beaker, all of those sugar crystals are touching the water all at the exact same time, so they're all colliding all at the exact same time. So increasing surface area has the same effect as increasing concentration. And it has that effect because essentially more of the reactants are touching each other at one time. And so increasing the concentration means it increases the number of collisions. And the more collisions you have, the more likely you are to have effective collisions, so the rate increases. And if the rate increases, the time required decreases. Rate goes up, time goes down. Then we have nature of reactants. And nature of reactants is a little bit tricky because it's not something that you can change yourself. Nature of reactants is just what types of things you're reacting with each other. So if a particular molecule has really strong bonds within that one reactant molecule, it's unlikely to be able to break apart easily to turn into a product. Or if it has more of the bonds, then it's going to be harder for it to break apart into the products. So the stronger the reactants hold together themselves, then the slower the reaction. Also, if two different types of molecules have the same type of bonding, they will react faster. So polar things will dissolve in polar things, and nonpolar things will dissolve in nonpolar things. But oil and water don't really mix because oil's nonpolar and water is polar. So this is not something that you can change. I can't make water nonpolar to get it to dissolve in oil, but it's just something to be aware of. The way the reactants are bonded to each other and the type of bonding they have compared to the products will affect how fast it reacts. And the last one we have is a catalyst. So a catalyst is something that increases the reaction rate by lowering the activation energy. And we're going to talk about activation energy in just a second. It's how much energy it takes to get the reaction started. So what you really need to know about catalyst is it provides an alternate pathway or a detour. And it does not affect the value of delta H, which means it does not change the starting or the ending point. Sorry about my handwriting here. So imagine that you are trying to get to our school and you're driving down the highway, and here's the road that gets to our school, and here's the highway, lots of people on the highway. And so you and your little car are about to turn and go on the street so that you can go straight to our school. Well, here's the problem. There's an accident right here. Oh no, you can't get by. So you decide to do a little U-turn under the highway, drive down the feeder road, turn into the city another direction, drive down that road, turn the other direction, drive past the firehouse, drive through all the streets, and you end up getting to the school. Now, that second path took a lot more driving to get to the school. But the thing is, it ended up being faster because you didn't have to sit for, I don't know, how many hours waiting for that car accident to finish. So it provides a detour, a different way to get there, which may sometimes look like it's going to take longer, but would actually take less time depending on what your reaction is. Okay, here is just a couple of terms for you to know. One is activation energy. That's energy of activation. That's the minimum amount of energy needed by a molecule to react. The higher activation energy means a slower reaction because there's more energy to overcome. So let's just say you are walking, and you're going this way and you decide to start running. Run! And so that takes a certain amount of energy. But let's just say you are sitting in a nice little chair. Pretend like this is a chair. And there you are sitting in a chair and you decide to run. So the first thing you have to do is get up, and then you can run. It will take more energy to make you get up before you can start running than if you were starting by walking first. It takes more energy to go from a sitting position. So this has a higher activation energy before I can get started with my running, and so then it will take me more time to get started with my running because I have to stand up first. Last term to know, oh wait, not quite last, almost last term to know, is the activated complex. That's an unstable transition state between the reactants and the products. It occurs at the highest point of energy. So here I'm going to give you a reaction to look at. Let's just say we have hydrogen and chlorine, and it's going to make hydrochloric acid. So let's just say my hydrogen molecule looks like this. We've got two hydrogen atoms that are connected together. And my chlorine looks like this, two chlorine atoms that are connected together. And let's just say hydrochloric acid looks like this. And those get erased. Okay, so there's my hydrochloric acid. So an activated complex is a transition state between the reactants and the products. So I'm going to erase it and draw it all over again and talk about the activated complex as we're going. So again, my hydrogen molecule is two H's that are connected together. And my chlorine molecule is two Cl's that are connected together. So the first thing that happens is we get a bond between the H's and the Cl's. That is your activated complex. That's kind of like the middle ground before you can get from the reactants to the products. That thing doesn't really exist, it's just kind of our middle ground. Because the next thing that happens is that these bonds go away, and there's our products. So our activated complex is when the four of them are connected. It occurs at the highest point of energy. So now let's talk about that in terms of a catalyst. So a catalyst provides an alternate pathway. We'll go back to our reactants. So maybe with a catalyst, instead of the first thing that happens is that the H's and Cl's connect, maybe the first thing that happens is the H's and Cl's disappear. And so here in your, the bonds between the H's and Cl's disappear. So here your activated complex would be 4 individual atoms. And then the next thing that happens is bonds appear again, and there's your products. So a catalyst provides an alternate pathway, a different way to get from your reactants to your products. All right, here's our last vocabulary term to know, and it's delta H, or heat of reaction or enthalpy. Write this down, it's not in your notes. It's the amount of heat that is gained or lost over the course of the reaction. So starting at the beginning, does it overall gain heat? Does the reactants take in heat? Or overall, do the reactants lose heat or give off heat? So it can be calculated by products minus reactants. So how much heat is in the products? Heat in products minus heat in reactants. It's the amount of heat in the products minus the amount of heat in the reactants, so that we can see how the amount of heat has changed over the course of a reaction. All right, that's all your vocabulary terms to know. The next thing we're going to do is the graph and look at a reaction rate diagram. So here's a reaction rate diagram, and it can be 2 different ways. It can be endothermic or exothermic. So we'll start with exothermic because that comes first. So we always start at the beginning of our reaction with the reactants. That's the beginning. And so then those reactants have to gain a certain amount of energy. That's my activation energy to get to like the top of this hump. It's like the top of a roller coaster before you can get your roller coaster started. Once it's gotten there, then it can make the products. And here's my products at the very end. This is an exothermic reaction. Exo means loses or gives off. And thermic means heat. Again, sorry about that handwriting. So exo means loses or gives off. Thermic means heat, so this loses heat. Notice how the reactants are higher up than the products. They go down before they get to the products. My delta H, which is the difference between the reactants and the products, it's just how much it loses or gains over the course of the reaction. And again, activated complex, that's the highest point of energy, this transition state. And only one other thing in this picture, that is the catalyst. A catalyst is the alternate pathway, so that's this dashy line that I've just kind of drawn over top of. That shows that you don't have to get quite to as high of an activation energy before you can make your products, so it should make the products overall quicker. So this graph on the left is exothermic because overall it starts high and it ends low. The other one is endothermic. So an endothermic reaction, again, starts with reactants at the beginning and products at the end, because reactants react to produce products. But notice that it overall goes up instead of down. Endo means takes in. And thermic means heat. So endothermic means it takes in heat. The reactants have to go up to get more heat before they get to the products. So my delta H is still the difference between my reactants and my products, where the reactants and products started and ended, but this time my delta H is going to get larger because we're going up. Activation energy is how much energy it takes to get started, so it has to get to the top of that hump from here up to there before my reaction can get started, and then it falls down to make the products. For a catalyzed reaction, I only have to get up to there before my reaction can get started, and then I make my products. So let's see how you can use this reaction rate diagram to find out different things about a reaction. Okay, so this is the exact same graph you had just a second ago. I've just taken the arrows off to make it a little bit easier to look at. And this time we're going to put some numbers with it. So let's pretend that the products down here are at 10, and then up here we have, say, 50, 60, and 70, just to make up some random numbers. So what is the activation energy for the forward reaction? Activation energy is how much it takes to get the reaction started. So we start at the reactants and we go to the highest point of energy. 70 minus 50 is equal to 20. Okay, what is the activation energy for the forward catalyzed reaction? Forward means I start at the beginning. Catalyzed means I'm going to the top of this dashy line. And so this time I have 60 minus 50, which is equal to 10. Okay, activation energy for the reverse reaction. Well, in reverse, we're starting at the end and going to the highest point of the hump. So now we have 70 minus 10, which is equal to 60. And then for the reverse catalyzed, reverse means starting at the end, but now I'm only going to the top of the catalyst hump. So that's 60 minus 10, so that'll be 50. Okay, delta H, now that's a different beast altogether. Delta H has to do with how much energy it takes, gains or loses, to get from the reactants to the products. So notice I'm going from 50 down to 10. So in this case, I will have 10 minus 50 to give me a negative 40 for my delta H. Delta H is the only thing that can possibly be negative. For activation energies, always just take the bigger number minus the smaller number. But for delta H, I'm going to make it a negative 40 to show that overall the reaction is losing that heat. Remember earlier when we were talking about delta H, we said it could be calculated by products minus reactants. So 10 minus 50. But if you're looking at it in reverse, delta H for the reverse reaction will be starting at products and going up to the reactants. So that would be 50 minus 10, which gives me a positive 40. Delta H is the only thing that could ever possibly be negative or positive. It's the only one where the sign really matters. And then finally we have energy in the activated complex. Remember, activated complex is just the highest point of energy, and so it's just plain 70 with no calculation. And for the catalyzed activated complex, then we're at the top of the catalyzed graph, so that'll be 60. So that's how you use the graph for calculations. Okay, so let's do that one more time. But this time with the endothermic graph, and I'm going to put different numbers on it just to give you a different thing to calculate. So let's say the reactants are still at 10, but this time let's say the products are at, oh, that looks like a 60 to me, and the catalyzed reaction looks to me like a 75, and the uncatalyzed reaction is definitely 90. Don't you guys think that looks like 90 to you? Okay, so what I want you to do is pause the video here and try these calculations on your own with those numbers that I just made up and see if you can come up with these calculations. Pause your video now. Okay, I hope you actually paused your video and stopped to calculate these things on your own, but either way, here you go. Here's your answers. Activation energy for the forward reaction. That means starting at the beginning, going to the highest point of the highest hill. That'll be 90 minus 10, which is 80. Then we have activation energy for the forward catalyzed. By forward, it means start at the beginning. Catalyzed means go to the highest point of the catalyzed hill. That'll be 75 minus 10, which is 65. Then we have activation energy for the reverse. So starting at the end, going to the highest point of the highest hill, that'll be 90 minus 60, which is 30. And then activation energy for the reverse starts at the end. Catalyzed goes to the top of the catalyzed hill. Start at the products, go up to here. That'll be 75 minus 60, which is 15. Remember that all of those activation energies are always positive. It's just the distance between the two, irregardless of whether you're going up or down. But for delta H, which is my next one, it depends on whether you're going up or down. So let's look at the next one. Delta H for the forward reaction, that means starting from the reactants going up to the products, it gains from 10 up to 60. So if you say products minus reactants, you get a positive 50. This time the positive counts. It matters that it's a positive 50 and not a negative 50, because that's showing that it went up by 50. However, if you're going in reverse, you're starting at the products and you're going down by, again, 50. So it'll be 10 minus 60, so that's a negative 50. Always show the sign for delta H, whether it's a positive or a negative, always show the sign. Then we have the energy in the activated complex. The regular activated complex is just the highest point of the highest hill, so it's just 90. But for the catalyzed activated complex, that's the highest point of the catalyzed hill, so that'll be 75. So that's how you use calculations with a reaction rate diagram. That's factors that affect reaction rate and a bunch of vocabulary words along the way, including collision theory and activated complex and activation energy and delta H. So I hope you learned something, and I'll see you next time.